Hello, everyone. My name is Cameron Krasovich. I'm a research technician and advisor down here with CSD working on alternative fuels and waste to energy systems. My background is in computer science and engineering.
Hello everybody, my name is Alex Perkins. I'm an engineer and sustainability teacher at CSD. I work with waste and energy systems and also research alternative fuels and how we can build off the biodiesel program. Our team's very excited to share the work we've been doing this semester with you.
I'm Jason Stillerman.
I'm Owen Cirilli.
I'm Dorothy Thompson.
I'm Michael Braithwaite.
I'm Charlie Bonsack.
I'm Maddie Eve.
And we are the Alternative Fuels team. Our research question this semester was, can we repurpose waste motor oil through centrifugation to supplement biodiesel use on campus? Motor oil is a lubricant used in engines that reduces friction between moving parts. After extended use, the motor oil breaks down and is no longer functional as a lubricant, and that is when you'd have to perform an oil change. What comes out of the engine is waste motor oil. Waste motor oil contains water, dirt, metals, and persistent organic pollutants. These have to be filtered out before the waste motor oil becomes useful. When waste motor oil is exposed to the environment, it has detrimental effects. Just 1 gallon of waste motor oil contaminates 1 million gallons of water. It also will seep into the soil and harms all wildlife it comes in contact with.
Traditionally, waste motor oil gets disposed of by getting re-refined into fuels and other lubricants, and it can also be recycled as or turned into an asphalt. This is only possible with resources and refinement facilities that unfortunately we don't have on Eleuthera. So people resort to improper disposal methods like simply burning the waste or dumping it outside after an oil change. Currently on SIDS, they're using waste motor oil as a termite repellent and a weed or vegetation killer. But unfortunately, again, people are still dumping it into the soil, which greatly harms the environment. Locally, we receive waste motor oil from the vans, generators, and boats on campus, and also from the 3 main power plants on Eleuthera, which all run on diesel. And the island school, as I said, the vans, boats, and backup generators all run on diesel, and that diesel costs $4.70 a gallon, which is significantly more than in the States. And because these vehicles are running so often at the island school, we produce 200 to 250 gallons of waste motor oil per year.
So after we get this waste motor oil in the vans on campus and from other sources on island, we have to clean it first in order to use it for our fuel mixtures. So the first cleaning process is called the settling process, and as you can see from this side view diagram, it uses gravity to separate out the water and dirt from waste motor oil. So the process actually works very well for the first half of the cleaning process, but doesn't really clean waste motor oil to the degree that we need it, that it needs to be cleaned for our fuel blends. And so we have to use the process of centrifugation to further clean the waste motor oil. And this system spins at very high RPM, which then forces the denser contaminants like sludge and water towards the outside of the system. So how this works is first, waste motor oil is pumped into the air pump, and then it goes into the heater, and we actually heat the waste motor oil so that the molecules are easier to separate, and then it goes into the basin of the centrifuge where there's a cone that spins at a very high RPM, and that RPM creates a very high G-force of 36 Gs, which is much more powerful than the G-force of the settling process, which is actually only 1 G, and that high G-force pushes those dense molecules of sludge and water towards the outside and bottom of the cone, and then those are collected as the sludge in our system, and then the clean motor oil rises at the top of the centrifuge and is collected as our product to the system. So we use clean motor oil in 4 out of our 5 blends. As you can see, each blend is a baseline of B50, which is half biodiesel. That's because on campus, our vans were already going to switch to B50 in all of our engines and vans, and so we wanted to increase the amount of clean motor oil, and our blends, we could decrease the amount of diesel we had to buy and use in each blend. And as you can see, each blend is labeled with the amount of clean motor oil in them. So for example, C10 is 10% clean motor oil, 40% diesel, and then the rest is biodiesel.
So after we made all these blends, we used different methods to test them to make sure that they would function well in a diesel engine. We tested them in two main categories. We tested them in terms of density, we measured the mass and volume of each mixture, and we also tested them in terms of viscosity. Viscosity is very important in a diesel engine. If fuel is too viscous, the fuel actually won't ignite and the engine will not run. So it's very important that the viscosity of our fuel blends fell within the range of diesel and biodiesel, commonly known as B100. And so for our results, we were looking for three main results. We were looking for our characteristics in terms of viscosity, density, and how well our fuel blends stayed mixed up after we mixed them up. We were looking for performance data in terms of brake-specific fuel consumption, which is it's a way we use to measure the efficiency of our fuel, to see how many grams of, we calculated how many grams of fuel would be able to generate 1 kilowatt hour of energy using our concrete mixer. And we were looking for economics of our system. We were looking to see if our system was cost efficient and saved us money as opposed to burning us more money. And so here are our charts for characteristics. The black lines indicate the range of diesel and biodiesel. As you can see, for density, all of our fuel blends fell within the diesel and B100 range, which is good. It was what we were aiming for. However, the C20 and C25 fell out of the range in terms of viscosity and most likely would not function well in a diesel engine, which is one of the reasons why we didn't test them.
So after we tested the characteristics of our fuel, the next logical step was to actually put our fuel into an engine to see whether or not our CMO would serve as a valuable supplement to the biodiesel and diesel. The engine we used was a concrete mixer we already had on campus. However, that concrete mixer was somewhat faulty, so we had trouble getting it to start as well as keeping it at a consistent rate for the entirety of our tests. However, the data that we did get indicated that the C10 mixture would be more efficient because the lower brake-specific fuel consumption actually means a more efficient fuel than the other three, which were all roughly the same. But because of our the faultiness of our concrete mixer, we still need to check all these values with a dynamometer, which is basically just a more advanced scientific tool for testing fuel performance. And then also we did a cost analysis of our system based on electrical, transport, labor, and maintenance. As you can see, the labor cost in our system is a very significant portion, so if we could automate the process, it would take us a lot less money to produce CMO. So as you can see, it takes us $2.55 right now to produce 1 gallon of CMO. So then we use that value as well as the cost of biodiesel and diesel to figure out the cost per gallon of each one of our mixtures. So as you can see, it goes from $4.04 to $3.72, depending on the concentration of CMO.
Okay, so with these numbers, we were also able to find our return on investment for each mixture, which can be seen over here. And we found that our return on investment for all mixtures was actually significantly fast. We found that even for our mixture with the lowest concentration of CMO, which is C10, our ROI was only about 6 months. And for our mixture with the highest concentration of CMO, which is C25, it was only 2.5 months, which is extremely fast economically. In comparison, the solar panels on campus take 5 years to earn our money back, and the wind turbine takes 23 years. So just to reiterate what we were talking about earlier about wanting our project to be cost efficient, this goes to show just how quickly we can make back our money on this project. So environmental impact. Eleuthera currently produces over 30,000 gallons of waste motor oil per year, and this is one of the power plants we visited that produces majority of this waste motor oil. If only 20% of that were to go into the ocean, it contaminates over 66 billion gallons of water, which is enough to cover the entire surface area of Rock Sound Bay. So area of Roxtown Bay. And by repurposing this waste motor oil on the island rather than shipping it out to, say, like the United States to go into one of their refinement systems, we're reducing the life cycle of carbon emissions because we were dealing with it on island. So moving forward, as mentioned earlier, we'd like to automate our system because majority of our costs do come from labor. So if we were able to cut down on labor costs, we'd significantly cut down on the cost of the project in total. We'd like to do larger batch testing along with looking at how the engine wears down over time with our various mixtures. And as Charlie mentioned earlier, we would like to use a dynamometer to further assess our fuel performance and just get more information in general about our different fuels. These are, we're excited. Acknowledgements, we would like to thank the Center for Sustainable Development, Kate Kincaid, Chris and Pam Maxey, and of course our research advisors, Cam and Alex. Any questions?
I'm wondering if that 78%, your highest cost for labor, if you were hiring people from the Lutheran community and if that was generating economic opportunity, is there any tax benefit that you would get from the government or something else to offset the high cost?
So the question was, if we were to employ people from the local community, would there be some sort of tax benefit from the government in order to kind of offset our labor costs? That's a fantastic question. That's not something that we looked into necessarily in the scope of our research, but that would also be something very good to look forward to for the projects in the future for next semester.
So given your findings that it seems to be efficacious to repurpose the oil, why isn't it being done in commercial facilities in the United States and other places? Why is it being used in asphalt and what CBD is always used for lower cost uses?
So the question was, if it's so great, why isn't everybody doing it? And there's a couple reasons. First, it's relatively new, the process of cleaning CMO. We did do read a study earlier about the Utah Valley University that was starting to do this, and they were kind of doing the same sort of process for the same reasons. But in addition, it's more advantageous to do it here because of the high cost of diesel fuel. So that's where we're making a lot of the benefit is by offsetting the cost of diesel. But since diesel is cheaper in the States and in other places where it would be easier to develop technology like this, it's actually less advantageous to use it because the diesel that you're offsetting isn't as expensive.
In addition to comparing the efficiency and cost effectiveness of this with solar or electric, did you also look at other alternative energies like wind or wave action or?
No, that was more of a, what? Oh, sorry. So the question was, did we compare it to any other renewable fuels or energies? And the answer was that wasn't really, the reason we compared it to the solar and wind was merely just because those are other similar projects on campus, and it was more a comparison of the return on investment than the actual project, because that was a good comparison.
With the amount of waste motor oil on the island, would the island still be able to commercially utilize some of that clean motor oil and sell it back to the island, or should you be able to consume it all yourself?
So right now, with the numbers that we were looking at was what? Oh, my bad again. So the question was, could we, based on how much waste motor oil they're producing on the rest of Eleuthera, could we commercialize that and maybe sell it back? I think you're asking. So we didn't really look that far ahead. Right now, we only use about, I think the number was 20,000 gallons of our blend on campus. So that would be kind of our cap at how much we would need. And then after that point, it would take more labor and more waste motor oil, which we could get to produce it. So in short, we could commercialize it, if we wanted to, but we haven't looked that far ahead.
The sludge, what percent is that of the original product? Like, so that 10% of, and then is there any, what do you do with the sludge, and is there anything that can be done with that?
So the question was, what percent of our original product comes out in the sludge, and what do we do with the sludge? The sludge actually only equates to about 5% of the clean motor oil. So even though there is still a byproduct of our system that we can't use, it's much less than the original product of waste motor oil, which is the other 95% of that. And so for now, we don't have a use for sludge. We don't have a use for sludge, but we're looking hopefully to think of ways to manage that problem in the future.
What was the level of interest from the local government in that power plant in developing this technology for themselves or in partnership with the island state?
Right. So the question was, what was the level of interest in this project from the local community? And we didn't actually communicate much with the local community. We did go out and talk with the power plant about more the waste motor oil that they produce, as opposed to implementing the project in other places. However, something we did consider is thinking about implementing the CMO into that the power plant, because in a power plant the cylinders are much bigger and they can handle a much more dirty fuel, so to speak. So our fuel blend might actually run better in the power plant than it might in a car engine. So going back to your point earlier, we were thinking about communicating with the power plant and maybe giving them an excess of CMO.
So the question was, are we currently using this blend in any of our vehicles on campus, and kind of like what our next steps are? So we have not yet implemented this blend into our vehicles on campus. The data that we've received is actually very recent, so we're still kind of collecting more data and trying to see how much information we can get on our blends, but ideally we would like to use this sooner rather than later, although as we mentioned earlier, they are implementing B50 in our vehicles on campus. And next steps moving forward, we've mainly just wanted to implement more tools to find out more about our fuels and just how efficiently they can run in the system, how much better we can make them using what we know, and we can really just never stop collecting enough data like on our fuels and learning more about what we have, and that's what we're looking at in terms of next steps so far.